I would like to take this opportunity to today share a few recent insights that we gained into planet formation with you, and in particular trying to address the issue or idea of forming planets given all the things that we know from Kepler. So when we try to understand how planets form, we are faced with the following challenge. So we have a really good idea about the initial conditions because we have these beautiful observations of disks around other stars. And we have a pretty good idea about the final outcome that planet formation theory should deliver because we know we do want to form something like our own solar system. Or we know that we have to explain how you form hot Jupiters, so planets as big as Jupiter, orbiting very close to their host stars. And since Kepler, we also know that we have to be able to explain a system that consists of multiple planets that have very tightly packed orbits, which can all orbit inside the orbit of Venus. So we have a really good idea about the initial conditions because of the beautiful astronomical observations of disks, and we have a really good idea about the final outcome. But we have much fewer observational constraints on how we get from A to B. And as you know, if you don't provide a lot of observational constraints, you can come up with a lot of theories explaining you how you could possibly get there. And some of them may be truly crazy. So we have to be a little bit inventive and try to see what are the constraints, and we have to try to use those to really learn something about the planet formation process. And so the first constraint that I'll be talking about today actually is related to the architecture, the period distribution or period ratio distribution from Kepler, and I will explain this more in a second. In the second half, or in the last part, I will be talking about something more related to the formation of terrestrial planets in our own solar system and their connection to the Kepler planets, and how we have some evidence into that process from actually highly pseudophile elements, for example, iridium and osmium. But first, before I jump into this, I would like to start with giving you an overview of kind of the standard planet formation theory, the planet idea that we have, how planets form, and then see how this may be different. So in general, in a nutshell, this is how we think planets form. Initially, we have the formation of planetesimals in the disk, and that's still one of probably the least understood phase in planet formation itself, and it's still a very active area of research. But assuming we actually do form these planetesimals, and that they're, who knows, a kilometer or maybe bigger in size, the next stage that has been identified to be important in planet formation is actually called runaway growth. It's called runaway growth because during this growth, the rate at which a body will double its own mass or its own size is proportional to its own size. So the growth rate is proportional to the radius. So it means the bigger you are, the faster you grow. And so if you are one body that's slightly bigger than the rest, you literally run away in size from all the other bodies in the system. That's why we call it runaway growth. Of course, many of you might be familiar with this because runaway growth not only happens in planet formation, it's also, for example, thought to be important in the formation of black holes, and there are many other examples. When can you get runaway growth? What's the key ingredient? Well, I told you need a growth rate that's proportional to your radius, so you get this runaway process. How do you get it? So in planet formation, the way you can get this growth rate is by enhancing your cross-section for growth above your physical size. So if you just have your physical size and you could only accrete things that are directly on a collision orbit with you, then you cannot get runaway growth. But if the velocity dispersions of the planetesimals that you're accreting is low enough, such that they feel the gravitational pull of the planet as they come close, the orbit is deflected towards them. And so they can be accreted, although they were not on a direct collision orbit. And so we call this gravitational focusing. So the planet is actually effectively increasing its own cross-section by its gravity. And this works, of course, only if the velocity dispersions of the planetesimals is less than the escape velocity from the body, because otherwise they can just whiz by. They won't really notice the gravity of the planet. And so the low velocity dispersion of the planetesimals is what allows you for this runaway growth. And it's quite nice because although the runaway growth is not very efficient in converting all of the mass into big protoplanets, it's crucial because it can form a few larger planetary embryos in a short amount of time. And in planet formation in general, it's always a race against time. Because we know from observations that gas, for example, the gas dissipate on a few million-year timescales, and we need to form planets as big as Jupiter in that timescale. And what is also nice about this runaway growth is that, for example, our Kuiper belt is thought to have been stuck at the end of this runaway growth. And actually, the observed size distribution of large Kuiper belt objects very nicely fits with our models of runaway growth. But let's continue. So after runaway growth, what happens next? So bodies grow, and they keep growing until they're so big that they, with their mass, totally dominate the steering, so the gravitational excitation of the planetesimals in their feeding zone. So in the annulus around the sun, from which they can accrete their material. So it's kind of what's kind of drawn here. So you have several protoplanets spaced in radius away from the star, and they're all responsible for dynamically exciting these planetesimals in their own feeding zone. And so these bodies now can keep growing by accreting those planetesimals until they reach what we call an isolation mass. So the isolation mass, you can calculate it in a very straightforward way. It's simply the mass that you would find if the body would accrete all the material in its feeding zone. And if you do that calculation in the outer solar system, you find that the isolation mass you get is roughly the mass of Uranus and Neptune, which is quite nice, because that means that Uranus and Neptune may very well be these isolation masses, so planets that essentially accreted all the material that was available to them in their own feeding zones. However, there is a problem. And the problem comes when you repeat this calculation. So for a while, we thought this is how planets form everywhere. But if you repeat this calculation in the inner solar system, say at 1 AU, you find that the isolation mass you get is only a fraction of the mass of the Earth, about a 20th. And so we know that then the Earth cannot have just been a simple isolation mass. So although the outer planets in the solar system, like Uranus and Neptune, may indeed just be these isolation masses, the planets in the terrestrial planet regions are likely not. And so instead, what we think happened to them is that they had additional phase of planet formation, is what we now call giant impacts. So what happens is you form several... Oh, thank you. Once you formed several of these isolation bodies, once they consumed at least half of the material and turned this into protoplanets, eventually, as these planetesimals are depleted, they no longer are able to collectively provide some damping to the velocity dispersions of those protoplanets. So these bodies start to excite each other's eccentricities and inclinations. And so what you now get is that their orbits start to cross, and you can have these giant impacts. And of course, our moon-forming impact is like the last giant impact that we think our Earth has gone through. So the picture for terrestrial planet formation is quite different from that for Uranus and Neptune. And then finally, there's actually one last stage of planet formation, which just consists of the cleanup of the leftover material. Often this is overlooked or not thought of a lot, but it's actually needed, especially if you had giant impacts, because you need something that can damp the eccentricities at the end of the giant impact phase back to something that's close to circular. Because today, if you look at the eccentricities of the terrestrial planets, they are very small. They're much smaller than you would expect at the end of giant impacts. And the best agent for doing that, I think, is actually the leftover planetesimals that remained, because they reside there for a long time, and they're basically eventually cleared out by accretion, or in the outer solar system by ejection. But they can provide this extra damping that I will come back to later. So I'm telling you all this because what I think the fundamental question that we would like to know is whether the planets, the vast majority of planets that have been discovered by Kepler, whether we should really think of their formation similar to that of Uranus and Neptune, or whether they had a formation more similar to the terrestrial planets with the phase of giant impacts. So you probably don't need to know here more about the Kepler mission, and you're probably all fairly familiar with it, but let me just summarize it very briefly here. So the goal of the mission was to detect Earth-sized planets around other stars. It was launched in 2009, and it's been taking photometric measurements of more than 150,000 stars with a 30-minute cadence. And it's returned a very large number of planetary candidates. I think we are up to more than 4,000 right now. And I think one of the truly interesting and exciting things that came from it is that there are many planets that reside on multiple systems. There are more than 1,000 planetary candidates that are in a system that has another planet in it. So they really like to hang out and have company. And remember, this is on fairly short period orbits. The median period is about 10 days. So this is only looking at the really most inner parts of those systems. So they likely have even more companions. But even on that fairly short time period, they really like to have company. They're not loners. And their typical radii are somewhat bigger than the terrestrial planets. The median radius is about 2 Earth radii. So what I've shown you here is the period in days of all the candidates in the Kepler catalog as a function of their radius as a fraction of the Earth radius. And so all the blue points are the data. And then for comparison, I plotted here Venus, Mercury, Venus, and Earth. So you know where they fall. And you can see that it still remains challenging to detect true solar system analogs, because this region here is still fairly empty. But what's more than apparent, I think, is that there's a vast number of planets that are very different from the ones we know of in our own solar system, with typical sizes somewhat bigger than the terrestrial planets that we have, and their orbital periods, significantly shorter. For comparison here, this red line corresponds to the radius of Neptune. So these planets are typically somewhat bigger than the Earth and often smaller than Neptune, but on, at least for now, on short period orbits, so what we would call the terrestrial planet regions. So should we think of these planets as really, bigger versions of the terrestrial planets in terms of their formation, or maybe should we think more of them like having formed like Uranus and Neptune, and then they must have migrated to their current locations because you could not reach these large isolation masses right there in situ. So one evidence, or one piece of evidence that we can look at is actually the period distribution of those objects. And that's what I've shown you here. So basically, this plot takes all the multiple planet systems, and it just takes the ratio of the periods of all the companions. And then it's just a histogram of that. And then for comparison, I've drawn here a few lines indicating some of the mean motion resonances of the systems. And I think the first thing you should see when you look at this plot, that there doesn't seem to be anything special in general about those locations of the mean motion resonances. These planet pairs fall all over the plot. So I think the zeroth order evidence, or zeroth order thing you should see is most planets are not in or near any of these mean motion resonances. There is, however, for a small fraction of planets, maybe 10% or so, they do seem to know about these mean motion resonances, and that, like for example here, the 3 to 2, and then more than an axis, there seemed to be a big deficit, just short of the 2 to 1. So like about 10% of the planet pairs seem to have some memory of those and are in or close to those mean motion resonances, although the period ratios are slightly bigger than the exact resonance. So what do these two clues tell us about their formation? What can we learn from that? Let me first tell you about what a mean motion resonance is. So of course, this is just a simple picture of a 2 to 1 mean motion resonance. So basically, you have two planets, and the inner planet goes around its star twice in the time that the outer body goes around once. And they keep meeting again at the same position in the orbit. How do those resonances work? Why is there something special about such configurations? So you can simply understand this by looking at these two planets again. So you have an outer massive planet, and then we on a circular orbit, and we have a smaller, much less massive planet on an eccentric orbit. And if you now look at the interactions, so if they always meet in resonance, if they always meet, so they are in resonance, in a 2-to-1 resonance. So if they always meet either exactly here or here, either exactly at pericenter or epicenter, then you can see that the torques experienced just before and after are completely symmetric, so there's no net force on the system. However, if you now look at a point of conjunction where they meet somewhere over here and examine the symmetry, you see that this exact cancellation of the symmetry you had before is broken. And so now if you look at the position just before, you see that there's a slightly larger force before conjunction than after conjunction. Because before conjunction, there's a slightly smaller distance between the planet, the big planet and the small planet. This distance is slightly smaller than here because these orbits diverge. Furthermore, the interaction time is slightly longer before conjunction than after conjunction, because here the relative velocities, the difference in their velocities is less than here because this inner body is speeding up towards pericenter. So because you have a slightly larger force for acting for a slightly longer time, the net effect is that you add angular momentum to the inner planet, so you expand its orbit, so its period becomes longer. So the next time these two planets will meet, the inner body must have traveled slightly closer to periaps than before. So instead of meeting here again, they would meet somewhere closer to here. And so now as homework, you can repeat the same thought experiment on the other side of this. And what you will find is that, again, the angle of conjunction is driven towards pericenter. And so if you would now only plot the position of conjunction of the system, you would get something that looks like this. So this is only the position at which they meet, only the angle at which they meet. And you see how it was driven towards pericenter and then back towards pericenter. And if this motion looks very similar to you like a simple pendulum, then you of course are correct, because it turns out that you can actually you can capture the full complicated equations of resonant interactions with a very simple pendulum analogy. So that's why I brought you a pendulum. So it's really just like the pendulum motion. For comparison, I wrote like the standard pendulum equation for a simple harmonic oscillator that I'm sure you all love up here. And you can compare this with the equivalent version for the resonant equation of motions. And you see that they will be identical apart from one factor. And this is this additional factor you have here. And this is because it's not a simple pendulum. It's a pendulum on a slightly magical string. And the string of my pendulum is magical in the following sense. So in the normal pendulum, you just have this motion, in which case you would just have a simple swimming to and fro. So there would be no width to my banana. So this width of the banana comes from the fact that my string is magical. And it's magical because the length of the string depends on whether I'm swinging left to right or right to left. And how longer it is depends on the velocity that I'm going at. Okay? That's the only magic about it. So once you account for that, it's a simple harmonic oscillator with a slightly magical string. What's the magical string in my planetary system? Well, the lengthening of the string comes entirely from the fact that you're actually in a rotating frame. So the Coriolis force around the sun gives you that extra lengthening of your pendulum and shortening as it swings to and fro. In any case, the only thing that you really need to know for the whole rest of this talk is that if you catch two things in resonance, that you get a solution to these full resonant equations that correspond to nested periodic orbits. So you just can fully solve for the orbit that the other planet should have. The only relationship that is important is that the eccentricity that orbit has is inversely proportional to how far you are away from exact resonance. So as an example, so say I have two planets. They're migrating relative to one another, so they're coming closer and they're caught in resonance. When I'm say 0.1, when I have a period ratio of 2.1 instead of exactly 2, I'm already in resonance. I have an eccentricity. But now if I move from a period ratio that's 2.1 to 2.01, so I'm closer to exact resonance, so that delta A, that I'm away from resonance, decreases, my eccentricity goes up. So it goes from, say, 0.01 to 0.1. So that's the only part that's important. So the eccentricity you have is inversely proportional to how far you are away from exact resonance, that delta A. So if you're exactly in resonance, when your period ratio is exactly 2 to 1, this delta A would be 0. So what this means is the following. If you have planets in a system and you have convergent migration, so these two planets' orbits approach one another such you can get capture and resonance, what that means is you capture your planet in resonance and migration will keep pushing them closer and closer. So in resonance, the eccentricity of the planet will grow. It'll keep growing until it reaches of order unity and then escapes from the resonance. That's the only interaction you have. So the one key thing is that the time it takes for the eccentricity to grow in the resonance is the same time scale it takes to migrate in the disk. So it's the migration time scale. And of course you can show this numerically. So that's what I did here. So I assembled a lot of planetary systems and I just let them migrate relative to one another. And they beautifully were caught in resonances. These are all these humongous peaks here. And you can see roughly that the area in these peaks is kind of more or less equivalent to all these little wiggles down here. So overall, if I look at a large number of planetary systems, I should see a roughly equal number of planets in the systems that are in resonance compared to out of resonance, if migration was important in their formation. And of course, that is not at all what we see in the Kepler data, and that's drawn here for comparison with these in this like slightly, red wine color. So there's something we're missing. And so one of the conclusions that people actually have drawn from this is that these planets must have formed in situ because if they had migrated in the disk, you should have had all these resonant pairs that you don't see. However, I think the solution is simpler than that. First, let me show you. So the simplest thing you can think of, well, maybe they were not very suitable for being captured in resonance in the first place. Maybe there was something special about them or about the disk. But if you look at which planets should have been caught in resonance, which I'm showing you here, so this is basically the disk mass you have. So that what matters is the local disk mass because that gives you the rate at which you migrate. And you need to compare that with the rate for resonant capture. And what you find is that all the area in the yellow regions are ideal for capture and resonance. And you can see, especially at an AU, Earth and Neptune-sized planets are ideal candidates for capture and resonance. If you would go further out in the disk, not so much, because the migration would be too fast for low-mass planets to be caught in resonance. But at an AU or less, where we're finding those planets, there would be caught in resonance, no problem. So there's something else. And I think the solution to this is actually quite simple. And it comes back to the disk. So the same gravitational interaction that the planet has with the disk that leads to its migration also leads to the damping of its eccentricity. So it's the same physical interaction. So if you now include not only the migration, but as well as the eccentricity damping in the equations of motion, the whole dynamics change completely. And you can kind of already see why from just the one thing that I told you, that the separation from resonance is inversely proportional to the eccentricity. Because if I now have something that can damp the eccentricity, then you can see there can be an equilibrium where the damping of the eccentricity is strong enough to balance the growth that the migration wants to give it, growing larger and larger. And indeed, you can show analytically that this equilibrium exists. And not surprisingly, it's just given essentially by the ratio of the time scale for the eccentricity damping over the time scale of the migration, which I'm calling here tau E and tau N. Here, tau E and tau N. And a numerical factor, which is not very important. Furthermore, you can actually show that this equilibrium, so this is my pendulum, this equilibrium, actually can be overstable. So if you actually perturb the system slightly from this equilibrium, you can actually get growth because it's overstable. So what does it mean to be overstable? Overstable means that if you perturb something away from equilibrium, that the force bringing it back brings it back at a velocity larger than it had as it was going out. So instead of just being damped back down to equilibrium and settling back down, what this leads to growing and growing librations until the system becomes chaotic and escapes the resonance. The nice thing is whether or not these overstable librations exist only depends on how massive your planet is compared to this ratio of the damping time scales. So it's very simple. And that's what's given here. So what we find is for not so massive planets, so if mu, which is the planet mass divided by the star mass, is less than this, which is just essentially a number given by the ratio of the eccentricity damping time scale to the migration time scale, you are caught in resonance, but you get overstable librations. Your librations grow until you can escape the resonance. If you're for more massive planets, so if your masses are bigger, you are instead damped to the stable point, and you just sit at this equilibrium, happily ever after. And the only other thing that's really interesting and important is that the growth timescale for these librations, for these oscillations to grow, is given by the eccentricity damping time scale and not the migration time scale. You know, before I told you, if you have no eccentricity damping, you spend about the time scale it takes to migrate in resonance, because that's how long it takes to grow the eccentricity. Here, to grow these librations, it only takes as long as it takes to damp the eccentricity, not the migration time scale, but the eccentricity damping time scale. So there are actually 3 different outcomes depending on how massive your planet is. If you're like Jupiter, you're all the way up here. And what you see here, this is a integration showing the period ratio of 2 planets. You have a Jupiter migrating, so they're migrating relative to one another, and they're caught in the 2-to-1 resonance. And then they sit there happily ever after, as expected, because their librations are damped and they're stable. If you now repeat the same exercise with a Neptune, you find again, you can catch them in resonance, no problem, but their librations grow, but to a finite value, and then you're stuck in resonance happily ever after. If you now repeat this exercise once more, but you choose an Earth, or something that's a few times the mass of the Earth, what you find is, again, catching in resonance is not a problem, but your librations grow, and they grow and grow and grow until they're so large that they actually escape the resonance. So the difference between these 3 planets would be Jupiter would be boring like this. Neptune would have some growth, but it would be finite in amplitude. And for the Earth mass planets, you'd have some growth, and it keeps growing until you escape the resonance, which corresponds to, in the pendulum model, from having growing oscillations until you change into circulation, in which case you have broken the resonance. There's no more resonance lock, and you pass through the resonance altogether. It's really beautiful. There's a simple 3 different analytical criteria for these very different outcomes. And I was very surprised that people had not, in the past, noticed these overstable librations or derived these criteria. We did spend a considerable time looking at what people had done also numerically, because we were a little bit worried that people hadn't noticed this in numerical simulations. But it turned out that most studies that had been performed were in a different parameter space, so usually actually in the one up there, that you are caught in resonance, but you stay there happily after. However, we did find one study done by Jack Wisdom and his student Jenny Meyer for the evolution of the Saturnian satellites, and they indeed noticed that under certain conditions they could find overstable librations. So they noticed numerically that there was something interesting going on in their system. And so this is the analytic criterion for having those 3 different outcomes. So this is just summarized here once more. For example, so Jupiter's, it's not surprising. So for example, GJ876 is a nice example of Jupiter mass planets being caught in resonance and being stuck there forever, because it consists of a system of half a Jupiter and 2 Jupiter mass planets, and will be fully consistent. I would also predict that the system would stay in resonance forever. But the Kepler planets, they are more in this size range, and most of those will not be caught in resonance forever, and they should escape this resonance on a time scale that's given by the eccentricity damping time scale. And so this is interesting because if you ask, what's the eccentricity damping time scale? How does it compare to the migration time scale? How are these different? Well, although each of them depends on how much mass you have in the disk, for example, on the semi-major axis, and so on and so forth, the ratio, because it's the same physical interaction that leads both to the migration and the eccentricity damping, the ratio of the eccentricity damping time scale to the migration time scale only actually really depends on the scale height of the disk to its semi-major axis. So that's quite nice, to the square actually. So typical disk scale heights are about 10% of the radial extent. So that means that the eccentricity damping time scale is about 100 times shorter than the migration time scale. So for our planets, that means the following, that planets that Kepler typically finds, they are caught in resonance, but they spend a time in resonance, which is 100th of the time they spend migrating in between the next resonance. So it therefore should not be surprising that only a small fraction of planets are seen to reside in or near mean motion resonance at any moment in time, because they only spend 1% of their total time in those resonances. It's not that they're not caught in them. It's not that they don't know about them. It's just that they only spend a short fraction of the total time in them. So we can now test this. We can look at the actual data. So what I'm plotting here is the mass ratio of the planet pair. And then this is the ratio of the more massive planet to the star. And so so if you have mean motion resonances with dissipation, which we've been investigating here, then you predict that if all the Kepler planets, or most of them, fall in this region up here, which says captures, those planets would be captured permanently in resonance and stay there happily ever after. So if all the Kepler points would lie up here, we should be really surprised that most Kepler systems are not in resonance. Then it really would tell you that disk migration cannot have played a major role in their formation. If most of them fall down here, then their masses are so small that although they are caught in resonance no problem, they'll escape on a short time scale, on the eccentricity damping time scale. And so it should not be surprising to us that most of the planets seen and found by Kepler are not at any moment in time, when we look at the data, reside in or near mean motion resonances. They would only spend about 1% of their total time there. And then there's this interesting kind of region in the middle. These are these Neptunes I was referring to. These are the bodies that can be caught in resonance and undergo finite amplitude growth, and they could stay there for a very long time, maybe forever. And whether they exist probably depends on where you are in the disk. So first let me plot the data and I'll tell you a little bit more about them. So this is how the data looks like. This is from the Kepler planets. And you see that most of them fall in the region where you do not expect you expect resonant capture, but they won't reside in resonance for a long time. Only 3% of the time if you actually calculate it precisely. So we should not be surprised that only a small fraction of Kepler systems are in or near mean motion resonances when we look at the data. And so it does not, this paucity of mean motion resonance systems does not imply that they have to have formed in situ. You can still have migration, significant migration in the gaseous disk. These here are interesting because those bodies will have finite amplitude librations and can stay there for a long time, provided that the damping is weak. Basically, the damping time scale is much longer than their libration time scale. However, when you do this for really close-in systems, because the time scales are very short, we find that for several of them, the eccentricity damping time scale is comparable to the libration time scale, in which case the simple analytic model doesn't quite hold and many of those do escape. However, if you would go further out in the disk where the time scales are longer, there's a good chance to find some of those systems still undergoing librations in resonance. So much about the resonance. I told you that there was this other interesting observation that although only like 5 or 10% of planet pairs are seen to be in resonance, the ones that seem to be in resonance have period ratio that are slightly larger than the exact resonance value. So how's that? How can that be? And so you can see, actually maybe already from this, that just the resonance itself is actually not symmetric. And so if you randomly sample where you would find a planet at a given moment in time and measure its period ratio, you do get a systematic offset in the right direction, just from the resonance itself, without anything else. However, the magnitude of this offset is not large enough for the typical planet masses to give you a 1 to 2% offset that's seen in the data. So that you need something else. And that something else is best provided by some dissipation. You need something that can damp the eccentricity. And that goes back to the simple equation that we were using earlier, that the eccentricity in the resonance is inversely proportional to the distance or separation from exact resonance. So if I can decrease my eccentricity, if I can damp my eccentricity, I can increase the period ratio, the delta A, the separation from resonance, and then I'm good. So what's the best way to increase my eccentricity? So I should say, until just now, we were talking about a stage when there was still all the gas around. And this outcome won't change very much, because as the gas dissipates, because all these outcomes only depend on the ratio of the eccentricity damping to the migration timescales, it won't change what category your planets fall in. So it shouldn't change this outcome. So if you look much later in the system, what else could give you the damping? So the gas is all gone. But I think the best candidate to give you some additional dissipation, some additional damping of the eccentricity, is actually leftover planetesimals that still reside in the regions. And we have actually evidence from our own solar system for such a leftover planetesimal population. So for once we have, of course, the Kuiper belt and the asteroid belt, which are filled of planetesimals left over planet formation. And then we also have something for the terrestrial planets, which is called late Vernier. So basically, we have some evidence from geochemical elements, measurements, that there were some planetesimals left over in the terrestrial planet region that were accreted late after the giant impacts. So we have some evidence for these leftover planetesimals in our solar system, and I think they would be the perfect candidates to provide you with this extra eccentricity damping that you would need to get this offset. So I thought I'd tell you a little bit more about this late Vernier. So how do we know? Why do we think that there were planetesimals left over in the terrestrial planet region after planet formation, after the last giant impact? So this evidence comes from highly pseudophile elements. So these are elements. They're called highly pseudophile because they're iron-loving. So they would love to hang out with iron. So if these elements had been accreted to the Earth before the core had formed, so before the last giant impact, then all this material would have ended up in the core because they'd love to hang out with iron. However, the fact that we find them in the Earth mantle is interpreted that this material was delivered to the Earth after core formation finished, so after the last giant impact. And so, like examples of these highly pseudophile elements are iridium and osmium. And so you can measure their abundance in the Earth mantle, and you can calculate how much material that is, and you find it's about 1% of the mass of the Earth is inferred to have been accreted after the moon-forming impact. And then you can repeat the same exercise for rocks we have from Moon and Mars, and you find that in terms of relative ratios that the Earth accreted a few hundred times more, so maybe 150 to 700 times more material as late Vernier compared to the Moon, and the Earth accreted about 10 to 20 times more material as late Vernier compared to Mars. So that's the evidence, the geochemical evidence we have that really these leftover planetesimals existed in the terrestrial planet region. So of course there is this other reason that we would like to have them, not only for the exoplanets, that's a third reason. But the other reasons for the terrestrial planets, I told you, would like to have these bodies left over because we need something to damp the eccentricities after the giant impacts. And this is because people realize that if you run these numerical simulations to form giant impacts to form the terrestrial planets, you form the right number of bodies, but the eccentricities are always too high. So it was realized a long time ago that adding small planetesimals will help you get lower eccentricities. And you can do a very simple order of magnitude estimate. How much mass do you need in these small planetesimals to give you that eccentricity damping to have circular terrestrial planets at the end? And so the minimum mass you need is just given by requiring that the time scale for damping the eccentricities has to be shorter than the time scale it takes to accrete those leftover bodies. Quite simply, if I accrete all my bodies before I damp the eccentricities, I didn't get any damping. So that's the very simple criterion you can write down. And if you do that, you find that you need at least 1% of the mass of the Earth in small planetesimals to give you that damping. So I thought, oh, that's pretty nice, because that's kind of more or less consistent with that 1% that people estimate the Earth accreted as late Veneer. So then you can go one step further and ask, could you explain the relative amounts of late Veneer delivered to Earth, Moon, and Mars? Right? Because we also have an idea of the relative amounts. And I think the short answer is yes. But it does give you a limit on the sizes of the planetesimals. So if you just take, again, simply the physical sizes of those bodies, the amounts they should have accreted relative to one another would just be given by the ratios of their radii squared, right? There's nothing, it's just the cross sections. And that, of course, is very inconsistent with the data, because for the Earth and Mars, this ratio would just be 4 compared to 10 to 20, and for the Earth and the Moon, this ratio would be about 20, but it's observed to be at least a few hundred. So that would be not consistent. So that doesn't seem to be the way that this material was accreted. However, if we go back to what we were talking about earlier, if the lossy dispersions of the small bodies is actually small enough, so you can not only accrete the bodies that are on a collision orbit with you, but you can also accrete bodies because their velocity dispersion is small enough, they gravitationally are focused towards you. They feel the gravitational pull of the Earth. Then you increase the accretion cross-section by this gravitational focusing, and now the ratio of the effective amounts accreted by the Earth and Mars no longer just scales as the radius squared, but will scale as the radius to the 4th power. So if you do that for the Earth and Mars, you find that the relative amounts accreted should be about 17, which nicely falls in the observed region. And if you repeat this simple exercise for the Earth and the Moon, you get a number of around 300. Of course, which again nicely falls in the observed region. Of course, the case for the Moon is slightly more complicated, because the Moon actually resides inside the gravitational potential of the Earth. So you can do a slightly more sophisticated calculation, but the answer is very similar. So the true value instead of 300 turns out to be about 200, but nonetheless, so you can explain the relative amounts delivered as late Veneer as long as the velocity dispersion of those planetesimals that are delivering it is less than about 1/10 of the Earth's escape velocity. And so that just gives you one more limit. How do you maintain such a low velocity amongst those planetesimals? I think the simplest way to do that would be by collisions. So if you have no other way of damping the velocity dispersions of those small planetesimals, and you need collisions, that will give you a limit on the typical sizes, an upper limit on the sizes of the bodies that delivered most of the late Veneer of a few tenths of meters. So in short, what we observe as late Veneer can indeed have been delivered by the same planetesimals that you would like to appeal to have been there to give you the damping of the eccentricities after giant impacts. And you can explain also the relative amounts of late Veneer delivered, provided that the bulk of the late Veneer, most of the mass, was delivered by relatively small bodies. And I think it's likely that something similar, a similar leftover planetesimal population, probably is responsible for giving you the extra offset that you need to explain the observed planet pairs in mean motion resonances found by Kepler. So let me just summarize. I presented you a simple model for orbital resonances that includes dissipation. I showed you that, so we discovered that you can have overstable librations, and which is quite nice because it can explain why even if you had a lot of migration in the disk, you would expect most Earth to Neptune-sized planets to not be in or near mean motion resonances typically, if you just take a snapshot of several systems in time. It does give you, this resonant interaction itself does give you a systematic offset from exact resonance to larger period ratios. However, to explain a 1 or 2% observed magnitude of this offset, you need some additional damping. And I think a leftover population of planetesimals is probably the best candidate for providing you that additional damping after this disk has disappeared. There may be a few systems, especially larger periods, and for maybe Neptune-sized planets that may still display some large amplitude librations, and that's something that we're looking for. So basically, I think the small number of planets currently found near or in mean motion resonances cannot be taken as evidence for in situ formation, and we will see, but my guess right now is that this migration likely played an important role in shaping the architecture of the systems that we see today. So thank you very much.
So if I understand this correctly, and maybe it was in one of the plots and I missed it, but you would expect that there would be an overabundance of more massive planets near the resonances compared to out of the resonances. Is that correct?
Yeah, so let's see. So actually, it's slightly more complicated because there are two contributions. Yeah, unfortunately, I didn't bring that plot. So there are two contributions. The ones that we see in resonance, there are two contributions. They're the ones, the small, lower mass planets that just happen to pass through, and you just happen to look at the system or freeze the system when they were just passing through. And in addition, there's a fraction of planets that really should hang out there in the long run. Yeah, and so we find actually there are these two contributions. And I think, if I remember, so I think they should be roughly equal in magnitude, because this will tell you that about 3% of the time they spent in resonance, and the other one would be another few percent. So so there are these two components to it, but the ones that should be caught long term should be more massive, at least compared to the star. So the ratio of the planet to the star should be the more massive. And unfortunately, I didn't put this plot here. I did do a plot that actually included more planets up here, and where I plotted the ones that are in or near mean motion resonances, and there are several of those here that really are indeed look like they are the ones that are caught there forever. And then there are several down here which seem to be the ones that we see them there today, but more or less by chance because we caught them on their way through. Yeah.
So if you just plot the ones in the upper right corner, are they more clustered near the resonances?
Yeah, exactly. So unfortunately, I didn't put this plot in here. So basically, if you plot the ones here, and then I colored the ones in green that are near resonances or in resonances, you find that a very large fraction is. And of course, they may not all be in resonance because we're not sure that all of the systems had the conditions for convergent migration. Because typically, the migration rate scales as a planet mass, and so to have convergent migration, you need the more massive planet to be on the outside, and so it's not a given that you had the chance to catch all of them ever in resonance to start off with, but a large fraction of those are.
So what did you assume to get masses for these Kepler planets, and how can that affect your results?
Yeah, very good question. So what I did something very simple. I took the radii from the impact catalog, and I assumed they have a density compared to Neptune to get the masses. And so there is an uncertainty, so these numbers can change slightly. But you can see, it's a pretty big region, so to really change the statistics, you would have to change the masses by a lot. But I'm very open to suggestions to get more precise masses, because for most of them, we only know them roughly.
the lake veneer, did that happen after the crust formed? Because if it did, are these 40-meter diameter things strong enough to break through the crust?
Yes. So the true answers we don't truly know. We don't truly know whether they were accreted before or after the crust formed. That's talking to my colleagues in EAPS, they think probably you would mix them. But we are actually looking into this in a bit more detail because they think this 1% might be an underestimate of how much mass was delivered because they feel that there was still a lot of mixing in the mantle and you may have delivered some of them still close to the core or in the lower region. So we're trying to understand if there's a little bit more you can say and do on this.
I was wondering, on the Earth you can use plate tectonics to mix from the core, from the crust into the mantle.
That's right.
Not on the Moon or Mars.
Yeah, so on the Moon, I don't remember exactly all the details from Mars. On the Moon, I totally agreed. So on the Moon, the biggest uncertainty from the Moon comes from the fact that we only have a few rocks, and we have to somehow assume that those few measurements are kind of representative. So of course that's a challenge. So it's like the opposite of astronomy. We can measure often many things like roughly. They can measure a few things like super precisely, but how do you interpret this? No one really knows. But and then the other. But assuming that there are. There is the one uncertainty is that, of course, you had also many bigger impactors, and that kind of causes some, which is sometimes termed gardening of the Moon. So there's some mixing just in the regolith, and so that can hide some material, or that especially because the heavier material seems to. People think that the heavier material tends to sink to the bottom, and so when you only collect some rocks from the top, there's some uncertainty there. But it's not. I don't think it's a. I think it's a much smaller uncertainty, and of course you cannot really hide the same amount of material you could on the Earth. So I agree. And also, that's if anything, I think that would make the relative ratio higher than lower. Yeah.
This plot, of course, is for planets. Most of these are the ones that are inside the orbit of Mercury. So from what you showed. Is it different for? I'm thinking of Jupiter and Saturn, which ought to, it seems to be in the upper right.
Yeah.
What's up? Is that a totally different scenario?
No. So for planets like Jupiter, so let's see. So there are two things that are different. So for more massive planets, those you can actually permanently capture in resonance. So there is actually some planetary system known to have like Jupiter mass planets. They're still on short orbits, but they're Jupiter mass planets caught in the mean motion resonance, in the 2-to-1 resonance, and they just sit there happily ever after. And you can integrate the orbits beautifully, and it all makes sense. So we know examples. So Jupiter and Saturn will be better candidates for permanent capture in resonance.
Well, that was my question. Why aren't they? Because they aren't in the solar system.
And then so there are two things. And then whether or not you can be caught in resonance, but depending on where you are, it depends on the disk mass. And there was this plot here. So that shows, so if it depends on the planet mass, so the planet, how fast they migrate, assume you have a given disk. How fast the planet migrates depends on the disk mass and the mass of the planet. And so the larger mass planets migrate faster. And so this plot here shows that whether or not you can be caught in resonance depends on basically where you are in the disk. So I took here like a simple disk where it was like hundredth of the mass of the sun. And then this would be roughly the local disk mass at 10 AU and this at 1 AU. And so you see that for planets that are at 5 AU or 10 AU, that Jupiter and Saturn, their migration rates are such that they are not good candidates for being caught in resonance, because you can only be caught in resonance if the migration rate is slow enough, or you have to go up in planet mass. That's this trade-off. So that's why. And actually, it's a nice prediction, although currently difficult to test. That means if you can extend your sample of Neptune-sized planets to like 10 AU, you should find they should have much fewer resonant pairs, because for them catching them in resonance would be very hard because they would migrate too fast. Yeah, so that's, I think, is the reason.
There are no more questions. Let's thank Hilke again.